And we're thrilled to have with us David G from Synadia, one of our gold level corporate members, who are going to be joining us today to discuss simplifying industrial automation with NATS. By way of a brief background, David G represents Synadia. He's a solutions engineer, got a lot of deep domain expertise in the space. And without savaging his bio, I'll let him maybe introduce his broader interest in the IoT space. So with that, David, I'm going to turn the floor and the stage over to you, sir.
Thank you very much. Hello, everybody. Welcome to this session. So for the next 30 minutes, or give or take, hopefully I'm going to convert you in thinking about NATS with industrial automation and simplifying your stack. So Synadia is an independent software vendor. It was founded some time back by two people. One of them is Derek Collison, the creator of NATS. He created that back in 2010. NATS, I'll go into more detail in a moment. Again, I'm David G. So I've kind of been on some of the pendulum swings. I started off in the kind of back end of the 90s in instrumentation, process engineering, and electronics. So way before Raspberry Pis and way before Arduinos, and actually built some kind of mini PLCs, and then spent 20 years in networking as well. So I would consider myself an enthusiast and a distributed communications technologist. I love machines, and how they talk to each other is nothing short of brilliant. So I think I'm fairly well experienced and placed to give this talk. If you've got any questions, please fire them across. I'll try and answer them real time, or if there's time at the end, we can answer them. In terms of where you can get some of the goodness that I'm going to talk about, if you wait till the end, there's going to be some links. If not, you can hit us up on the NATS community Slack. So with that, I'll transition to the next point. So let's talk a little bit then about NATS. So NATS, even in the team, we refer to NATS in many, many ways, whether that's a connective substrate, whether it is a data fabric. We've got so many names, but I want to keep it really, really simple. NATS for industrial automation performs a number of functions. One of them is communication brokering. One of them is persistence, but it gives us the ability to communicate in different kind of patterns. And some of those are request reply patterns, that are a little bit like HTTP semantics, like a GET. We can do pub sub, so we can have something publishing data and 0 or more things subscribing to that data. And then we can turn on persistence, and then we can do things like key value stores. We can do data streaming, and we can have object stores. And what it allows us to do ultimately is replace multiple components with one, and that has many effects and compound effects of reducing the amount of skill that you need to run all of these components in your infrastructure. NATS itself has been around a while. So if you've never heard of it, this isn't a kind of overnight technology that's come out of nowhere. We've been around for, like I think 13 years from its creation. There's over 300 million downloads, 30,000 GitHub stars across the repositories. 7,000 Slack members on the community Slack, and it's growing. And every week we kind of celebrate those numbers, and actually saw an email earlier on as well. I think we've just had the first million month on NPM as well, which is an incredible feat. And there's over 1,000 contributors again across all of the repositories there. I did say in Synadia, I'm part of the NATS team. We do some of the maintenance on the NATS ecosystem. We're not the only ones, and we're very grateful to everybody obviously that contributes. It is written in Go, and the NATS server and the clients are open source as well. So we've had some interesting comments, even in my short tenure at Synadia, especially around performance benchmarks and things. There is no closed magic here. It's not like a car engine or a famous German manufacturer that will remain nameless. So I'm just going to jump on to a drawing canvas here to go into a little bit more detail around NATS. Most of this talk is going to be on industrial automation and the communication patterns for that, but I just want to tip off some of the iceberg or tip of the iceberg conversations. So NATS is written in Go. When it's compiled, I think it's about 15.6 megabytes today, so let's call it circa 16 meg. We're currently on version 2.9.15, 2.9.10 is being worked on. And there's going to be an announcement around that. Now, the interesting thing around NATS is we have a single server image. So if we talk about NATS clusters, NATS superclusters, NATS leaf nodes, it's the same image configured in a slightly different way, formed in a different topology. It's multi-tenanted by design. We don't have to do anything weird to achieve that, and I'll go into more details. We use PKI extensively as well throughout the system, and that's important for the thing below, which I'll go into in a moment. Public keys make it onto the NATS system. Seed keys and private keys don't ever make it off the system. We can share data between different kind of tenants. We call them accounts, and everything therefore is authenticated and authorized. And we also have TLS for data in flight, so it's encrypted, and data at rest can be encrypted as well. Now, all of that's a very long way of saying we can run NATS in a very simple way with no authentication and no authorization. It's great for doing exploration. But we have these kind of patterns, and one of the patterns is decentralized authentication and authorization. So we have then this concept of an admin kind of umbrella account, which then can create accounts synonymous with applications, and then applications can create users or connections. And that's really, really important to understand. I'm coming straight out of the gates here with some details on NATS, but once we get these building blocks into place, so much more makes sense. Then we can have a conversation around clients. So clients synonymously kind of means the libraries and the client library. So we've got Go, Python, Java. I'm not going to read them all out, but we've got loads. So we've got officially supported clients, and then we've got the community ones. There's over 40 now, I think 45 on the last count or more. But we've also got a CLI client, and the CLI client is super useful because we can use it to do benchmarks, but we can also emulate every single style of communication pattern that NATS allows us to do. And you're going to see that in the demo later on as well. How are we doing for time? 24 minutes. Cool. We're doing well. So what you're seeing now then is a NATS cluster. So we have 3 NATS servers in a full mesh kind of topology. And then we have a NATS leaf node connected into that cluster. Now, you'll notice we've got an odd number of 3, and that's when we turn the persistence layer on, it uses RAF to basically distribute the state. So we need an odd number to get quorum. Now, the leaf nodes are interesting for many, many reasons, but A, they give us some survivability. So they're very, very lightweight, which means we can have a NATS leaf node live alongside client code on, say, like a single board computer on something very, very small. And if we have like microservice patterns that rely on NATS, let's say if there is a WAN disconnection, all of those blobs of software can run independently until the WAN connection is restored. I'll go into that at a different time. There's lots of good content on NATS leaf nodes, but from a topological point of view, we can talk about clusters using the same server. And then the clients can either initiate connections to a cluster or a supercluster or through a leaf node. And that's really, really important. Note that I didn't say the NATS servers need to know about the downstream clients. So as the networking gets muddier, and what I mean by that is cellular providers, wireless ISPs start running out of address space in IPv4, and IPv6 is very slow to emerge from a kind of proliferation perspective. We end up in a position where data is coming from an exploded number of devices, or like a data explosion. Device count and the amount of data that comes from the bottom is increasing just in astonishing numbers. So we need the data to go to the logic. And the idea is that we can use NATS, and we can build out these clusters and superclusters and whatever patterns deem right for your business. And then we can put the data into NATS and use NATS as a distribution mechanism to put the data where it needs to be. So we can put logic in smaller units, whether that's microservices style kind of approach to industrial automation, or we can rebuild our notion of what SCADA looks like. The supercluster pattern is interesting, by the way, because you could have a cluster on AWS in different regions. You could have one on Azure, one on Oracle, and it gives you basically survivability of your entire system and kind of performance gains and everything else. So let's jump from here to Industry 4.0. And I love this term, standardized access to machine data. We've already kind of mentioned that there is a flip of kind of data acquisition. So instead of enterprise networks being extended down to the data source, the world we find ourselves in, and as a number of devices increases, data has to come to us or come to the logic. And this is exactly what you're seeing with this CPS system in front of you. So we've got this, labeled as a PLC. It doesn't have to be a PLC. It could be a single board computer, something that's been designed to do the job. The client, now we've been through the kind of client logic talk, it could be some bespoke code that talks northbound with NATS and then east to west with, your specific kind of, compute board, whether it be PLC or not. But the information makes its way to NATS. NATS acts as this kind of distribution system, and the conversations that these machines have, they're unnamed conversations called subjects. And NATS is kind of independent. Well, it's location independent. It doesn't really care where it is. And then the conversations are named. So for a client to connect to NATS, what it needs to know is where is one NATS server. Doesn't need to know about all of them. What's a conversation I want to take part in? And then do I have basically an authentication token, JOT, key or whatever to gain access to the system? If those things are met, then the client can connect up and have those conversations, or one or more conversations can take place across the patterns. Just realized my voice is dying. It's cold season. Anyway, this is really, really important for many reasons, but one of them is we can move the data to the ops team. So the ops team then, say within the factory floor, can keep an eye on their process, but also we can do things like burst into public clouds to do AI and ML model training using the same NATS substrate, the same NATS system. So we have this seamless and secure connectivity, very, very simple. NATS is unicast based. It runs on IPv4 and IPv6. It has named conversations. So the networking is simple. Therefore, data becomes our operational currency from an industrial point of view. And then NATS really is just one reusable component. So we can talk about things in the kind of Industry 4.0 lens. Horizontal and vertical integration is easily achieved. Everything is secure by its very nature. So again, data in transit is secured by TLS. We can have data encrypted at rest as well. And then we can make sure that connections, so the clients as they connect to NATS, both are authenticated and authorized. And then we can do things like scope signing keys, which basically means we can do key rotations, or if we lose a key or if we're compromised, we can change one of the signing keys, which then automatically invalidates southbound connectivity, which is really, really important. Imagine somebody breaking into an electricity grid distribution system, stealing some keys. We need to recover from that. So we can't have long-lived keys. Anyway, I digress. Because we're flattening the landscape, we're removing etcd, we're removing Redis, we're removing Kafka, the amount of skills that you need to maintain and operate this system drop drastically, and support for the system becomes easier. We've got one system, and obviously Synadia can help with that as well. But now we've got this data currency idea. We can pull data in real time from the systems, and we can put them into streams, these kind of ordered ledgers, or these intrinsically ordered ledgers, which means then we can feed them into a software system so we can simulate a full process, which is kind of interesting. And if we can simulate, we might want to improve. So then we can do things like train AI models and ML algorithms for, predicting problems, and also optimizing processes as well. But all of these things combined give us this ability to grow our systems. This challenge of extending the enterprise network south kind of goes away, and it's getting increasingly harder to do just because of how the device count is increasing. Now, I'm going to jump from here over to SCADA. SCADA, where do we go with this? So lots of organizations say, hey, SCADA's dead, but it's not. It's in use absolutely everywhere. So SCADA is supervisory control and data acquisition, and it's both an architecture and a pattern that organizations for decades, and there's a UK term for this, which is it's donkey's years old. It's been used for a very long time. And it's built into levels. And at level 0, we have sensors and we have actuators. So that might be, voltage. It might be temperature sensors. We might have actuators like motors and solenoids and pneumatic rams. So this is like hardware stuff that's not easily controlled by, cloud software. Then we have the level 1 devices, which are things like programmable logic controllers, single board computers with, a very constrained amount of work they can do or data that they can acquire and send onwards. And then level 2 is where we have things like our sim sets, or you will have like a human interface showing you a mimic of a process that's running or some decisions that have been made. And then higher up the stack, we have monitoring systems, like operations center style affairs. Now, SCADA has always been deployed in a very kind of rigid way. It's been deployed under a single factory roof, for instance, where the network's been very easy to deploy and manage. But then as devices around the edge are distributed, potentially in non-fixed locations, we don't know where they're coming from. They're going to be of a cheap internet connectivity, again, so from wireless ISPs or from cellular. It's very, very difficult to just keep extending that network downwards. And so we end up in this horrible position where we've got more level kind of hybrid level 1, level 0 devices that need to connect to blobs of logic at level 2 and level 3, and NATS really comes into its own here. So this is actually from a series of blog posts we've been working on at Synadia. But if we squeeze in a level 1.5, so between level 1 and level 2, and put a NATS substrate, and notice I've not done anything with clusters here or anything. We talked about that earlier on, but really importantly, NATS is viewed as just this kind of connective thing that we can stretch between many locations and many clouds and factories and whatnot. We can then acquire data through client-side code. So either the PLC itself might be able to publish data, or the single board computer, whatever, but we can get client logic that will go and poll for information and then publish it onto NATS. It might have a requirement. We might need to put it into a data stream for, kind of posterity. We might need to analyze that further down the line. But because we have this kind of data fabric as it is, we can publish data even if something's not interested. We can store information on NATS as well about the level 1 devices. So we can actually, list metadata. Here's a PLC, here's some information. And then we can also store objects as well. So much like a web developer will, process streams and maybe generate files for batch processing later, we can do all of this with NATS. And I think that's absolutely powerful and an enabling pattern as we get bottom heavy in terms of industry. So what I'm going to do next, hopefully this works. They say don't work with children and do live demos, but here goes anyway. So what we're going to do a little demo. I've got some sensors and they're publishing data 4 times a second. We've got a level 1.5 producer, which then pushes that data onto NATS. So I've already set up the NATS server. It's one server. The persistence layer is turned on, but there's no streams or anything set up. And we've just got 3 data sources from the level 1.5 producer. And then the client on the left-hand side is going to be the NATS CLI client. So some terminal time. So the first thing we're going to do, I'm just going to show you the value of having the key value store. So I'm going to do NATS KV and then, right, let's take a look. So NATS KV list basically tells us how many buckets have we got. So we've got a bucket called PLCs, and then we can do something like NATS KV get PLCs. You know what, let's not do that. I'm jumping the gun. So let's take a look at what keys we have in the bucket first. So NATS KV list the keys in the PLCs bucket. So we've got PLC 1. And now we can do this. We can go off. What I'm going to do, I'm going to dump the whole value out so that the NATS CLI client, which is what you're looking at in front of you right now, will it'll chop off some of the bytes on the end so we can put the data on the screen without blowing our scroll back buffer. So I'm going to push it onto JQ. So I've basically got a JSON document here describing the PLC. So this is, a blob of code has put this onto NATS. We've got PLC 1. It's a Siemens device. We've got some protocol and address information of how to reach it. We've got description. Oh, Evil Corp LLC. We've got a data sensitivity matter here. And then we've got the data that the PLC is going to be publishing. So we've got one instance here where we've got subject called barrier, it's type string, the range, okay, edge high, the port on the PLC the data is being acquired from, and we've got a description, apparently henchman break room light barrier. So, okay, and then we've got a 12-volt probe, and we've also got a 24-volt probe. So that's what our metadata is telling us what's on the NATS system. So then we can go off and we can go, okay, well, let's see what subjects are actually being published to right now. So this is a little program called NATS Subject Profiler, and I'm just going to run this because it just gives us a very, very quick view of the subjects that are appearing across the NATS fabric right now. But this is emulating just a bash command anyway. So what I can do is I can do NATS subscribe, and I can subscribe to edit everything, and I'm going to do headers only. So this is like turning on the hose pipe. Now on a busy system, you don't want to do this. So the tools like the one I've just showed you are nice and easy to see what's going on. But let's do this anyway. And we can see here, we've got a steady kind of influx of data, and we've got 3 different subjects that are being published on. Fantastic. So then let's take a look actually at what's coming in on the barrier subject. So we can do NATS sub barrier. And we're doing nothing more now than we're getting real-time information off the NATS fabric. Notice I've not logged into any device to go and get this. The device is already publishing through a client onto the NATS system. So I'm now retrieving this straight from NATS. So this is data as a currency. This is data as a commodity. We don't have to worry about affecting kind of constrained southbound systems. It's already on NATS, which is interesting. So let's have a look as well. We've checked out barrier. Let's just, out of curiosity's sakes, check out the other data. So we've got a 12-volt voltage probe that's all over the place, which is fantastic. And then let's check out the 24-volt one as well. Okay, so now let's imagine then that all of a sudden we've received a trouble ticket or an enhancement request from Mr. Overlord, I believe the ticket is from, saying he wants information on how many times the light barrier for the break room is going off from his henchman. I think, okay, so he's either under attack by Austin Powers, or his henchmen are being pretty lazy. So what we can do is we can add a stream to make this data persistent. So let's call it, henchman. Subjects, we want barrier. We're going to put this into file. So this is going to be a disk-based file, replication of 1, because I've only got 1 NATS server. Retention policy is interesting. We don't have enough time to go through all of this right now, but it's going to be a limit, and a limit can be, number of messages, number of bytes on disk, or TTL. So we're going to do that. Discard policy. What happens when our limits are met? Well, we're going to discard the old ones. Stream limits. I'm not going to limit the number of messages either in the stream or the subjects in the stream, or the size, but I am going to put a 7-day retention policy on there, and I'm just going to go through the rest of the defaults. And then we can do this. We can take a look at the stream. So we've now got 2 messages in there, and now we've got history of the number of times the barrier is being broken. So we can do things like this. We can view the stream, and it's going to do pagination. And notice now we've also got timestamps. The data itself didn't have any timestamps as it come in, but the NATS system is allowing us some basic instrumentation to put some timestamps in, which is kind of interesting. Right, so now we've got persistence. What can we do with that? Well, like with any other write-ahead log system like Kafka, we have to consume the data and do something with it. So further down the line, there might be some software that creates a pretty graph. And to do that, we need to be able to consume from the stream. Now, the interesting thing is, as we distribute our data gathering systems, we also want to distribute logic, and distributing logic comes with a kind of penalty. We want to deal with the kind of smallest amount of state absolutely possible. So if we can hand off tracking, say, sequence numbers and indexes off to the NATS server, then I think that's going to be a win. So let's add a consumer and call it, henchman. Let's delivery target. I'm going to go through some of the defaults. Start policy, all. Acknowledgement policy means if we pull a message down, then acknowledge that we've had it, so we can be reliable in terms of how we consume information. Replay policy is also interesting because we can actually just take everything as an instant delivery, turn the fire hose on, give us everything, and we'll worry about the timestamps and everything else. Or original is quite fun, because what we can do then is we can actually receive messages as they were received in real time, real space. And I've got other webinars coming up where we build a karaoke machine of all things. I'm going to take the defaults as well, and we're going to do it on the henchman stream. And then what I can do is we can play with the consumer. So we can do, I think consumer info henchman. Unprocessed messages 87. Okay, well that's fine. So I need to put another henchman on there. And then we can then subscribe to the consumer. So I think we can do sub henchman, and you can tell I've been here before. And I'm going to acknowledge everything. And then let's just take a quick look, because what I actually want, we can pull messages, we can subscribe, we can then acknowledge. But what we actually want to do is we want to do a NATS consumer next. And what that will do is it will basically pull down every single message, and then it will run real time in the background. So I'm just gonna give it a count of, say, 1,000, and once the consumer has received 1,000 messages, this CLI application will exit. But this will be good enough, and that's not working. Again, live demos, I don't know what I've done there. Henchman. All right, I haven't got time to fix that, but you get the idea in terms of we can build these consumers, and then downstream applications can basically put the onus of managing state onto the NATS server, which is kind of interesting. Other things we've spoke about are things like multi-tenancy built in. So I've already said that NATS conversations happen over named conversations called subjects, and we can have, account A and account B using the same namespace, so the same subject space, which is kind of interesting. So we could have hello subject on account A and hello subject on account B. So what I'm going to do is I'm just going to show you this kind of account isolation thing. So I'm going to do account sub and then threads, and then hello. So I'm going to subscribe to hello on the PLC1 account credentials. And then what I'm going to do is I'm just going to go to NATS pub threads PLC1, and then we'll basically say hello on the subject, and we've basically got the hello on the left hand side. Now, if I change a credential, so change the account and change a connection, we're still publishing on the hello subject with the same information. You'll note there's nothing appears on the left hand side. So what we've got is the conversations are named the same, but we have this separation of interest between multiple accounts, i.e. multiple applications, or using this NATS fabric, which gives us some superpowers. Right. So in terms of a recap then, so we have a number of sensors throwing information up to the producer. The producer pushes them onto NATS. We started off with information just making its way across NATS with nothing listening to it. We then added a stream to the barrier subject to make that persistent. So then we have some history we can go over and analyze what's going on. Mr. Overlord might want a graph of the henchman running through the doors. We can do that. We've added a consumer. I'll figure out why the consumer went wrong. It's not NATS, it'll be me. I've put in the wrong command line switch or something, why that didn't work. But the consumer will track what messages have been consumed by downstream applications, which means your application can crash, it can come up somewhere else, and the data consumption can carry on absolutely undisrupted. So hopefully this has been interesting for you. We've been through actually quite a lot of material in very, very little time. We've blown apart the SCADA model. We've introduced this notion of many endpoints at the bottom, delivering data to the logic that's gonna process the data. So there is a series of blog posts here, which goes into way more detail than we've gone in this kind of webinar. Part 1 and part 2 are published. Part 3 is coming out soon. The links at the top, we've got natsbyexample.com, is a really great site if you want to see how some of these things are done. Join our community Slack, so slack.nats.io. It's very lively, everybody's very, very friendly. And then Synadia, we can step in and help with consultancy, managed services, all the normal stuff you'd expect, enterprise agreements, and we're working on products to ease operations and management as well.